promised we'd talk to the organizers here, and we're trying to get the heat up a little bit in the room. I know that it's pretty cold here, and they're going to try to get it up, but it's cold in all the other rooms, so I don't know how fast that can happen, but we'll try. And I would like now to start with the afternoon session, and it is our great pleasure to introduce Professor Bukur as our next speaker. He is the Chemical Engineering Program Coordinator at Texas A&M at Qatar, and hosted many of the attendees at the 10th Natural Gas Conversion Symposium in Durban last month. Dr. Bukur has carried out fundamental research in FT catalysis both in industry, as he worked at Mobile, R&D, and in academia, where he had a number of permanent and visiting faculty appointments, mostly at Texas A&M at College Station. He has made a number of contributions in the area of FT catalyst development, reactor modeling, including fluid bed, slurry bed, and other applications of supercritical media. The title of his presentation, Pretreatment Effects Studies with Cobalt Monolumina Catalyst for Fischer-Tropsch Synthesis. Please help me welcome Professor Bukur.
Can you hear me in the back?
Yes.
Okay, I'd rather not use the microphone. Well, thank you to the organizers for inviting me. It's my honor to be here, and for your kind words of introduction. And also congratulations to Bert for his award, and I'm happy to be here, Bert. It took me a long time to get here. All right. So the topic is pretreatment effects that we did on cobalt. Did I do something wrong, right? This way, no. Okay. So but briefly, I'll talk about some previous studies to give you proper background and our motivation to do that, and then what we try to achieve, and then I'll talk about results that include testing in fixed bed reactor and some characterization work. The conventional wisdom about this is summarized on the first slide there, that in order to test the catalyst in a Fischer-Tropsch cobalt catalyst, you reduce it with hydrogen to metallic cobalt, which is considered to be the active phase. There are some words about using CO as a reducing agent, and generally it's considered that to be undesirable. There's some German work, early German work, and then DOE work, and after that I haven't seen much in the literature. I guess everyone thought that's not worthwhile pursuing. It's a bad thing. It gives you low activity and high methane. And then we have examples from the literature that showed how some short exposure to carbon monoxide during Fischer-Tropsch synthesis has bad effects on the performance. Activity goes down and methane goes up, okay? So that's done conducting Fischer-Tropsch with syngas, then cutting hydrogen flow, and relatively short time, just a few hours, and you see some consequences. And then we heard also earlier this morning that polymeric carbon, which can be formed on the catalyst, contributes to catalyst deactivation. That kind of is, as I say, a conventional wisdom that most people believe in. There have been a few studies that showed that using carbon monoxide containing gases may not be such a bad thing, okay? And it might result in some improvements in the performance. And one of them is a cobalt on zinc oxide catalyst, which was a CO pretreatment followed by syngas, and they demonstrated significant improvement in activity and selectivity, and we were able to confirm this qualitatively in our lab. We don't necessarily get the same type of improvement that they obtained, but yes, it is higher activity and it's better selectivity. Then Goodwin showed some work in 2002 that if you add a little bit of CO to hydrogen, that might improve activity, but this was done under methanation conditions, very high hydrogen to CO ratio, maybe 9 or so, if I remember correctly. Then we have a patent, more recent patent by Johnson Matthey, which claims that syngas pretreatment, just use syngas with the normal 2-to-1 ratio, can lead to improved activity and selectivity. So don't do hydrogen reduction, use syngas, and you can get the good activity and selectivity. And then we have work by in France, where they use hydrogen reduction followed by CO to form carbide, and then do hydrogen again, which presumably leads to formation of hexagonal form of cobalt, and while normal hydrogen is primarily FCC cobalt, and that was found to give higher activity and no changes in selectivity. So you get a better, more active catalyst. So that kind of gives some examples where maybe indicate using CO is not so bad thing after all. And then we have work by Bert Davis and his group, and they used CO pretreatment and hydrogen treatment, compared them in a stir tank reactor. It was what was cobalt on titania catalyst, I believe. I don't know, I think so. I had that on the slide, right? Anyway, so cobalt, oh, there it is, ruthenium, and it had a little bit of ruthenium promoted, there it is. And then they showed, okay, activity here, right, that's hydrogen reduction was higher activity than compared to CO reduced catalyst, although you have some respectable activity with CO alone. But the most interesting thing, well, okay, let's look at methane also. The hydrogen reduced catalyst gives you less methane, and CO gives more methane. So kind of some things are what the conventional wisdom tells you. You get lower activity and you get more methane if you use CO in the pretreatment. However, the surprising thing is here, with hydrogen reduction, they switched to CO, they call it even CO regeneration, and we know that's supposed to be a bad thing, right? I mean, catalyst gets killed. But here you see improvement in activity. Activity goes up, and not only that, methane goes down instead of going up. So things are a little bit different than previous literature seems to indicate. There was no characterization work done in this study, so this is just reaction study with this, these results, interesting results. Then later Bert and his group did make a cobalt carbide. This is unsupported catalyst, so they started with oxide and then converted it to carbide. That was done in a fixed bed reactor, and then they tested it in a stir tank reactor, this material, at typical Fischer-Tropsch conditions. Okay, so that we have kind of cobalt carbide there. They did characterization cobalt carbide, and you can see that the conversion is very low, yeah, at the beginning, yeah. And methane is high. You get a lot of methane. So cobalt carbide, low activity, and a lot of methane. Then they start increasing temperature. Okay, that was at 493. Then they increased the temperature, and activity went up as expected. And what is not expected, methane went down dramatically, right? Conventional wisdom is you have more methane at higher temperatures. But something is going on here, right? And then they changed the space velocity, reduced the space velocity, got even higher conversion, and stayed there for a while. And the catalyst is stable with this unchanged methane selectivity. And then at the end of the run, they went back to, well, I skip this point. They went to these initial conditions, 493 and 3 normal liter. Activity is low as it was before, but my golly, methane stays low. It's, initially it was 50%. So obviously, catalyst is undergoing some changes, and they did some characterization, extensive characterization, and they showed that you form some kind of metallic species during Fischer-Tropsch synthesis. So what this work shows that cobalt carbide is unstable at Fischer-Tropsch conditions, and particularly at higher temperatures. So that meaning this 523. Okay. Now, there's a here big fundamental question, if you will. If cobalt carbide is not active, and I start using carbon monoxide with a cobalt oxide, why should I have any activity? Huh? So here's what possibility, just on the paper, okay? I don't have characterization, and I'm not aware that people did that. So, okay, if I use CO, it's a reductant, it made cobalt oxide, right? And then further reduction, well, now you have two pathways. Does cobalt oxide give me directly carbide? Or perhaps I go for metallic cobalt. But even then, okay, maybe then further reduction of carbide, or rather maybe because it's unstable, I can carbide decomposes partially and gives me metallic cobalt. Or if I go through this path, then I get some metallic cobalt. But of course, with more CO, this should be converted to carbide. But again, does carbide decompose and gives me metallic cobalt? And we know, it's known, I mean, that cobalt carbide is thermally unstable, but I mean, in inert media. The question is this true in CO atmosphere? Because why would that metallic cobalt not react back with CO and give me carbide, right? Well, Bird's group showed that that is possible in syngas atmosphere during Fischer-Tropsch synthesis. They are creating some metallic-like species that they call, right? So maybe it is possible, right? So the question is, what happens if you use CO, not in a syngas? I'm talking before Fischer-Tropsch, right? Maybe that happens with the carbon monoxide. So that's why we decided to use CO as a reducing agent to see what's going on. Well, Bird did that already with a stir tank. So here we are talking about the different pretreatment procedures. We tried some others, and I don't have time to talk about all this. There are a few, I think 4 of them today. So we did the reduction at 250. And we did then CO followed by syngas at 250, then at 350 CO, and then we did syngas at 350. And we did some characterization with XRD and all that, and found different phases. And also to study the formation of carbon, we did temperature program hydrogenation and oxidation coupled with mass spectrometer. So that we are trying to see first what is the performance, and can we relate this performance to what we find in terms of carbon and phases by X-ray diffraction. Okay, so now catalyst was prepared by conventional incipient wetness impregnation, alumina support from Sasol, 15% loading, and usual not so exciting anything here, calcination, drying. Pre-treatment conditions are shown here in detail. Let's keep in mind that CO250 indicates the temperature of pre-treatment. Everything is done at atmospheric pressure. Then we have CO followed at syngas at 250. And we did that because that's what kind of BP did in their patent on cobalt zinc oxide. They did first reduction with CO, and then they did syngas. And then we did the higher temperature CO and syngas at 350. Okay, so I'll start talking about reaction results first, and then we'll talk about characterization, all right? So conditions are shown here, fairly typical for cobalt catalyst, and here are the results. Okay, so activity is generally low. The only one that has more significant conversion at these conditions is syngas pretreatment. And then the other thing, what about selectivity? Well, if you look at methane, I mean, that's the most important thing. All of them except CO followed by syngas give you pretty high methane, but this one gives low methane. No, it's an interesting result. Okay, just looking at that, right? It gives similar activity, but much lower selectivity. CO2, we don't make too much CO2. It is relatively low. Okay, so that are the findings, reaction findings. So now we did some characterization. If it can help us figure out what's going on. Okay, the BT characterization results are shown here. Alumina support for comparison is shown here. After pretreatments, there's a reduction in the surface area, and syngas gives the highest surface area. Pore volume decreases more or less, and then it's similar for pretreatments, except again syngas, which tends to be close to the alumina support alone. And the pore radius is about 5 nanometers for this type, similar to the original. If you look at the pore size distribution, you can see it's broader with syngas pretreatment, but there's this dominant, so it's essentially unimodal with that 5 nanometers. But if you look at the finer picture there at the smaller radii, you can't see that on this scale. There you can see some peak about 2 nanometers with after high temperature treatments, either in CO or syngas. So there's maybe some partial pore blocking or something with carbon. XRD, okay, XRD. This major and minor, I really is based on intensities and may not be accurate description. Okay, I realize that, but my co-workers decided to divide that way and kind of help our story later on. These are the major phases. Although I'm not claiming that that's quantitatively necessarily so. All right. So really, you have, almost every of them has cobalt oxide, partially cobalt oxide and carbide, and then cobalt, either FCC or HCP, right? Except that we're saying, well, after 250, you have mainly carbide and cobalt oxide. After CO followed by syngas, you seem to have cobalt predominantly, or the highest intensity. After CO 350, you have some hexagonal cobalt and another carbide. And with syngas, you have a lot of metallic cobalt, and you have some carbides and cobalt oxide. Okay, then we looked at TGA results and what happens during activation. That was done in thermal gravimetric unit, trying to simulate conditions that we used in reactors. So that's CO 250, right? We do ramping to get there and so forth. And you see a lot of peaks there, right? Going there, and then we hold for 3 hours. Here, that's a time scale. So here is a 250 isothermal reduction. While this shows you what happens to get 250, those peaks. And we attribute these peaks to either moisture removal, some cobalt nitrate decomposition, and then eventually at higher temperature, cobalt 304 to cobalt oxide, and during 250 for 3 hours, we have conversion to carbide and metallic cobalt. which of course it's supported by XRD results, all right? I don't have any evidence from TGA that I'm making this species. All right, so at 350, if we do a reduction at 350, again we have similar story, these residuals, moisture and all that. And then as we go to higher temperatures, we believe that's where we are reducing cobalt to carbide and metallic. And then at about 330, right, temperature, we start weight gain. We are not anymore losing weight, but we are gaining, and that's obviously some carbon deposition. And there's quite a bit of carbon, okay, from here to here. It's a gain about 25%. So a lot of carbon is there. We're doing CO reduction at 350, yeah, as opposed to reduction at 250. Then we characterize what type of carbons we may have on the surface by doing temperature program hydrogenation, followed by temperature program oxidation. We first see what can we remove with hydrogen up to 600, and then we repeat that, go to higher temperatures and hold at 900 for 1 hour. Okay, I think I can skip that. It just tells us that's from Sasso's work, telling you about different types of carbon. Some of that we heard this morning. And basically we use this information to identify peaks based on at what temperature, maximum peak during temperature program hydrogenation. So to differentiate the species based on this classification. And here's what we have. Okay, so CO250, yeah, you have only peaks at lower temperatures, and after that nothing happens, and those are attributed to surface carbon or possibly bulk carbon, so those low temperature peaks. Same things happen when you do CO followed by syngas. You have only low temperature peaks, and if you do either syngas at 350 or CO, then you start, maybe you have some peak smalls here that are these carbides, surface or bulk carbide, and then you have what is known as polycarbon, because the peak is around 500 degrees centigrade. So we do form some form of polymeric carbon with CO pretreatment or with syngas pretreatment. If we do that followed by TPO, right? So we did our TPH, removed whatever we did, right? So we followed methane peak there. Now we follow CO2, and you can see low temperature reductions, nothing happens. So we removed all the carbon during temperature program hydrogenation, and they are only bulk carbide surface based. But with high temperature reduction in either pure CO or syngas, we do get again this polymeric carbon, and even with syngas we have at 780, which would be ascribed normally as graphitic carbon. So we are making some heavy ones or whatever, if you consider that polymers of carbon. So we have different species. And if you try to do this, we were saying, well, it's something due to support, maybe CO disproportionation occurs on the support itself. If we do CO 350, no, nothing happens. So it occurs on cobalt, not on the support. Okay, so now let's try to put this together, right? What we found from reaction studies and what we find from characterization, and even we can draw some conclusions here, right? So here is the this, and again the first peaks or whatever, or after what comes as semicolon, are considered to be minor phases, and these are dominant phases. And this also shows what we found from TPH, TPO. So we do have low temperature, we have cobalt carbide here and cobalt oxide, so it's incomplete reduction. Okay, it's low temperature, not rising in only for 3 hours. And TPH says that the only carbon species is carbide. And with syngas following, we form some metallic carbon, okay, metallic cobalt, and consider the dominant one and a little bit of hexagonal. We still have some carbides and oxide, and TPH, you have carbide. When we do this CO350, with dominant phases are hexagonal cobalt and carbide, and we find we have carbide and polymeric. And the one which gives us the highest activity, we find predominant cobalt, both types, hexagonal and amount of carbide and cobalt. With that one, we have polymeric and even graphite carbon. Okay. So, if you look then what the kind of selectivity you get, yes, so the relation is that polymeric carbide favor high methane activity selectivity. That's either CO350 or C50, where you have polymeric and some cobalt carbide. Cobalt oxide, that is to say, complete reduction and very little metallic carbon, also favor high, and that would be the case of CO250. If you have primarily metallic cobalt and you don't have any polymeric carbon, then you can get low methane, which was the case CO 250 by syngas 250. Well, okay, I'm going to summarize here what we found significant carbon deposition, C reduction at here as soon as 300 degrees, the deposition starts and increases rapidly. Treatments at 250, they don't lead to formation of free carbon, only carbide. Results tell us that our surface carbidic species for bulk cobalt carbide, they after all treatments, and there is polymeric carbon after CO50 or seeing high temperature pretreatment to formation of polymeric. EPO confirms that and shows maybe that you have even some graphitic very high temperature. This for selective observations kind of repeats what I showed you on a slide where I put together core phases and results of PhD. So I don't think I will go through again. And the conclusion is that